Thank you for pointing out the lecture was not getting recorded. It is getting recorded now. Okay. So, talking about the flexible interdomain routing, if there is an attack going on and if you want to stop that attack, then it makes sense to drop it as close as possible to the source of the traffic or source of the attack traffic. Because if this type of traffic is, think about, the DNS amplification attacks that are very popular. You probably have heard about them in the mainstream media, which were, like responsible for huge outages across the internet. So if this network, and the goal of these attacks is to overwhelm your network so that you're not able to respond to some legitimate requests that are coming to your network, right? So if this network attack traffic is already in your network, then even if you drop it, you're already like losing on the opportunity of serving legitimate requests, right? So the attack is in some ways successful. So you definitely want some interdomain routing policies that let you drop this type of attack traffic as close as possible to the source of the attack or outside your network. So let's talk about how interdomain traffic control is enabled today. This is a slide, or this is a title that I used a couple of years ago, but mainstream wise, like most of the networks still use VGP. So I think this is still a fair assessment of like how interdomain traffic control happens today, right? So the way VGP works is that the networks are going to advertise that I have a route to a particular IP prefix, right? And we have so many IP prefixes, around 1 million IP prefixes in the internet right now. And like different network operators or network providers will advertise to their peers that I have a route to a particular prefix, right? And which basically means that there can be millions of advertisements, route advertisements that can be out there. But then there are some aggregations that happen. So like it's not as bad. But typically, a particular network will advertise that I have routes to a particular IP prefix to their peer, right? And in this case, level 3 and Cogent are both advertising that you can send, like, I have these routes for 10/8 and 10, like, so 10/8 basically means that the last, the first 8 bits of the 32-bit IP address is like its numeric value is 10, and like any IP address whose the first 8 bits match to 10, and it can be anything up, like the remainder 24 bits can be anything. So that means that it is representing total of 2 raised to power 24 different IP addresses, right? So it is saying that, okay, any traffic that is matching on this pattern of 10/8, I know a route to it, right? So now Google as a network, and this is just an example, right? So Google can make a choice that I will either send my 10/8 traffic to level 3 or Cogent, right? So say, for example, in this case, it decides that it wants to use level 3 for it. So this is how interdomain traffic control works, that you get these advertisements at the granularity of IP addresses, and then you make the decisions at the granularity of IP addresses or IP prefixes. And clearly, this is a bit inflexible, especially compared to the examples that we were looking at earlier, that when you're making decisions at the IP prefix level, then you're not able to differentiate based on, say, type of application. So some other meta information about the type of traffic that you want to send or apply the policy for, right? So the question is that how can we enable flexible network control, right? And now I think it's not really a genius thing to think about that. Okay, like we have been learning about programmable switches in this class already. We know that programmable switches are more capable than the conventional routers that were already deployed at Cogent and level 3 and Google. So why don't we just replace these routers with these programmable switches, right? Now we should be able to make flexible decisions, right? And we might be able to make decisions based on the meta information about the packet, saying like, okay, if it is video streaming traffic, then it should go to level 3. If it is non-video streaming traffic, it can go to Cogent, right? So even if all those traffic still belongs or uses the IP addresses that belong to 10/8 prefix range, right? So within that, I can actually have one more level of distinction and say like, okay, app video traffic goes to level 3, other traffic goes to Cogent, right? But it's not that simple, because what we're now talking about is that we should be replacing all the routers that Google and level 3 and Cogent have bought and replace them with programmable switches. Though programmable switches are cheaper, so it's not completely unreasonable to go this route, especially when the routers are going to get expired. But it is still a very expensive thing to ask, and also it requires changes to a lot of networks, right? So for this to work, you require all these other networks to also upgrade, right? Which is, not a very desirable thing, and not something that you want to start with, right? So as we will learn in this class, that Google and Facebook actually adopted or adapted the ideas that were developed in SDX to build their own, interdomain routing framework, which was using the ideas that we will be talking about in the SDX. But I won't say completely that it's impossible for a network operator to change their conventional, routers, Cisco, Juniper routers with programmable switches to do interdomain routing, right? So Google and Facebook have done that, but they have done that in, say, 2017, 2018. But in 2013, 2014, when people were talking about enabling software-defined networking for interdomain routing, it was still seen as not a very strong case. You don't really want to start with an argument that, okay, you have already invested billions of dollars in these devices, now just replace them so that you can enable this type of flexibility, right? So uh, the question was, how can we incrementally or enable this deployment in an incremental manner, right? So how can we enable this flexible traffic control in an incrementally deployable manner, right? Something which is incremental, does not require a radical change, and it is still deployable and has a huge impact. So that's where the internet exchange points came to the picture. And I'm talking about 2012, 2013. This was a time when internet exchange points were gaining a lot of traction across the globe, right? So maybe I should take a step back and ask you folks a question. What is an internet exchange point? You folks have read the paper, so you probably have some idea about what an internet exchange point is. So maybe this is a good time to take a small pause and think about what is an internet exchange point. Feel free to speak up or use the chat for that. Yes, anybody? I know a lot of you know about it because you submitted a review form for it, so you have a decent sense of what it means. Yes. Okay. Yes, I have some answers now. So I'm going to read them a bit for the students who will be watching the video lecture and they might not see the chat. So Marco says that is it a location where a large amount of networks all have physical connections? And Raymond says where different ISPs exchange information. And Maggie says where ISPs exchange internet traffic between the networks. So these are all correct answers. And as I was explaining earlier, that the way border gateway protocol works is that you have these different domains on networks. Think about Google, Cogent, Level 3, UCSB. These are all different administrative domains that are trying to interconnect with each other so that UCSB can talk to Google and vice versa, right? So all these networks are advertising what prefixes they own and what other routes that they know about, right? So UCSBs is, you can call it as a stub network because it is not providing connectivity service for anybody else. It just wants the connectivity service for itself, right? So those type of networks are called stub networks. And then there are provider networks. So Cogent and Level 3 are, really large scale provider networks. They are called tier 1 providers. So Cogent and Level 3 in that category, but you can think of other ISPs which are providers. So think of AT&T, Comcast. These are also, these are sometimes called eyeball ISPs because they're providing direct connectivity to the eyeballs, from the content perspective that you are the eyeball and then you are getting connectivity. So all these networks are trying to interact with each other, trying to advertise that what prefixes they own, their customers are using what type of IP prefixes. And if they are the transit provider, such as Cogent or Level 3, then they're advertising for their clients as well, right? So if, say, for example, UCSB is a client of Cogent, then Cogent will advertise that, okay, these are it will advertise UCSB prefixes, and it will say that I know route to these IP prefixes, right? So that's how this interdomain routing works. But for that to happen, these networks have to exchange routes with each other, right? So either these networks can have one-to-one connection with everybody, right? And there are more than 65,000 networks out there. So think about the complexity of setting this up, where you have to set up these, 65,000 plus different links with all kinds of networks whose physical presence is limited to a very limited geographical area, right? So it just makes things very, very complex. So the community as a whole decided that, okay, we will create these internet exchange points, or co-location points, where you can all come together, you can bring your router, and then we will use a layer 2 switching fabric to exchange traffic with each other, right? So this is kind of like a small history of the internet exchange points. And when all these routers were coming together, initially there were tens or twenties of ISPs in a particular location, and this just kept on growing, kept on growing. And in US, it is a very commercial venture, that like the co-location points, or the internet exchange points. These are all privately owned companies that are providing the facilities. So there is lack of uh, transparency in terms of which type of networks are present there, what type of capabilities are there, and who can join this type of network, right? So there is less information available. But this model took a very different route in Europe and a lot of other countries, where the public internet exchange points became a public entity, right? So anybody can join. There were very transparent rates available, that okay, if you want to go for plan A, then this is the rate. And plan A basically means that what is the the pipe that you will get, or what is the link connectivity that you will get, whether it is 10 Gbps or 100 Gbps, or terabits of traffic per second. So based on that, you are paying for it. And there were a couple of exchange points which grew a lot of popularity in Europe because of their geographical location. So some of these exchange points, say in Germany, called Decix. So this is the exchange point which was in Frankfurt in Germany. And because of its geographical location, it was providing connectivity between Asian ISPs, African ISPs, and North American ISPs, right? So it was really a good melting pot of different international ISPs coming together and exchanging traffic with each other. So our, when I say our, because I was one of the, author or creator of ISDX, or SDX. So, at that time, our thought process here was that, these large IXPs have a huge impact. They're actually exchanging traffic of the order of few terabits per second. And if, rather than trying to make all these individual ISPs change their routers, what if we just change one switch that is connecting all these routers together, right? So that is something which is very incremental, that you just require one thing to change. And one of the design constraints that we put on this problem was that we will require zero change, literally zero change from any of the participant, right? So if you are Google, Cogent, or Level 3, bringing a router to an exchange point, the system does not or should not require these participating routers to do anything extra, right? So that was kind of like a design goal that was out there. And here, to enable that design goal, the idea was that we can replace this switching fabric with a programmable switch, and replace this route server with SDX controller, right? So now you might be wondering, hey, what is route server, right? So route server is nothing. It just offloads the control plane or processing that is required for border gateway protocol, or BGP. So think about it this way, that if you are at an exchange point, and if there are hundreds of other networks or ISPs that are out there, then rather than trying to create an individual BGP session with each and every participant, maybe you can create a BGP session with the route server, which will act as a proxy, and share or forward the advertisements from individual participants to you, right? So for every participating router, the threshold or the control plane overheads are significantly reduced, because now you're just interacting with one entity rather than interacting with all participants in the network, right? So this was the purpose of route server. It was a control plane tool which was used for scaling the BGP or the control plane interactions that happen at such locations, right? So compared to this type of model of exchange points, the SDX idea was to replace the switching fabric with a programmable switch, and replace the or subsume the functionalities of route server. So whatever route server was doing, it is still going to do the same set of things. But in addition to that, it will also enable software-defined networking in this framework, right? So it will act as an SDX controller. All right, so this is, by definition, it's kind of like incrementally deployable, because now you're talking about changing just one switch and replacing or upgrading just one server, right? So, and that is influencing hundreds of participants or providing flexibility for hundreds of participants that are present at an exchange point, right? So clearly building such an SDX is challenging. But before we move to that, I would just give you another chance that, like, if anybody has questions about the SDX in general, that what is an SDX, what is a control program, anything else, this might be a good time before we jump to the challenges of building an SDX. So can I assume everybody understood the point here? Okay, I think we can move forward now. Thank you. Yeah, so one question is, the question is that would an SDX still be in the same physical location like regular ISPs? Yeah, so I think, like, the only thing that is changing here is that we are replacing the switching fabric with a programmable switch, right? So it's the same physical location, just replacement of devices and the controller that is controlling those devices, right? I would also like to add, one layer of complexity here. So this is, like, I'm representing here one physical switch, and that is for the sake of exposition to keep things simple, right? But in real world, an exchange point won't have just one switch, right? So it is a switching fabric, meaning that there are multiple switches that are providing a layer 2 connectivity for all the clients, right? So it is possible that, like, a simple way of thinking about it is that there can be, rather than one switch, there can be two switches, right? And half the participant connect to one switch, half the participants connect to the other switch, and then like there is connectivity between these two switches, right? So the key point here is that whenever, say, Google's router is talking to a level 3 router, it will be a layer 2 connectivity that the exchange point is providing, which means that the IP address that you will see, like, the next IP address that Google will see if it is sending traffic to level 3 will be the IP address of the level 3 router, right? So there is no IP address for the intermediate infrastructure that the SDX or IXP is providing, right? So it is just a layer 2 connectivity. Is that part clear? Any confusion here? Okay, I think we can move on. All right, so on paper it sounds very easy. Just replace one switch, one server. That should be as simple as that. But then there are a bunch of research challenges that one has to address to make it real. So one is about the programming abstraction, that how will you let networks define these flexible control programs, given that this exchange or this switch that we are programming is shared, right? So there are different domains, each of them have different set of goals out there. So how will you make sure that they're not stepping on each other's foot, right? That's something which was important from programming abstraction, that how do you isolate the behavior of individual participants to the exchange point, given that physically they're still using the same switch, right? And as you can imagine, given your exposure to Pyretic, you can imagine that ideas about abstract topologies that were developed for Pyretic will be very relevant in this context, so that like provide the isolation, provide some abstraction such that there is isolation between the flexible control programs expressed by say Google versus what is expressed by Cogent, right? And the second question is about the interoperation with BGP, that even though we are making some changes at an exchange point, but everybody outside this exchange point is still using BGP, right? And BGP is still, the de facto protocol that everybody is using. So we want to make sure that when we are providing this extra flexibility at the exchange point, this is not coming at the cost of breaking global routing, right? So you should not be breaking things in a sense that, oh, I provide this flexibility, but then nobody else is able, like, you are able to reach some network with high flexibility, but nobody else is able to reach your network, right? So we don't really want to break those things, and how that can be broken and how that can be fixed is something that we will discuss in next few slides. And then there is a question of scalability, that we are talking about an exchange point where we will be having hundreds of peers or ISPs providers that are present. We're talking about at least 500,000 prefixes to work with, and talking about these flexible rules or flexible programs that are trying to match on multiple header fields, right? So we're talking about a huge scalability challenge, given that if we want to make all this work in just one switch, right? So let's start with the programming abstraction challenge. And given your exposure to Pyretic, I think this might be easy to intuit. So this is an STX switch. This is a physical switch. Now, if Google and Cogent want to write two different types of policies, one says that if source port is 53, drop the traffic. The other says that source port is 53, then it should be forwarded to level 3, right? So this is an interesting case that, like they are all both matching on the same header field, but they have two different type of actions specified. So how will you make sure that this action by like this program expressed by Google is only applied on traffic that is received or sent by Google, and vice versa for the Cogent, right? So if I let these network operators directly program the STX switch, right, using open flow rules, that will just create conflicts, right? So the switch won't know whether it should be forwarding the traffic to level 3 or it should be dropping the traffic if the source port is 53, which means if it is a DNS traffic, right? So how can this problem be resolved? This problem can be resolved with an idea of virtual switch abstraction. It's very simple, intuitive, that rather than letting these network operators directly program the physical switch, STX provides them an abstract software switch that they can, or the virtual switch that they can work on, and their policies will be applied on those virtual switches, right? And now for every packet that is coming in, these policies will be applied in sequence, right? So for example, there is a traffic which is say coming from Cogent, then it will arrive at this Cogent's virtual switch. Whatever are the policies on the Cogent's virtual switch, think about the DNS traffic that is coming in, right? So DNS traffic comes in at this virtual switch. Cogent says that if it is DNS, which means source port is 53, forward to level 3. So now that traffic is going to go to the virtual switch of level 3, which is where the policies of level 3 are. Then whatever are level 3's policy, then those policies will be applied, right? So as you can see that this is basically sequential composition of policies on demand, right? So you are matching on what is the input, and then you're applying Cogent's policy. And then based on Cogent's policy, if the output port is level 3, then this is going to level 3, and then the egress policies of level 3 will be applied, which are expressed in the virtual switch, right? So this is kind of like sequential composition of policies expressed across different virtual switches, right? And this is, all like the implementation of this idea is all based in Pyretic. Pyretic provides this type of abstraction where you can create these virtual switches on top of a actual topology, where in this case, it's just one physical switch. But then it lets you so then it's not exposing Google what other policies are out there and how those policies have to be expressed. Like they don't have to resolve conflicts on their own. All these conflicts resolutions, if any, can be done by the STX controller. So now the second challenge that we were talking about was interoperation with BGP. Let's try to understand how global routing can be broken if we are not careful here. So this is a very simple example. Google has a program which says that if it is destination port 80, forward that to Cogent, right? So port 80 is HTTP traffic, right? So it is saying that if it is an HTTP traffic, it should be going through the Cogent. And here, notice that we have two networks, level 3 and Cogent. Cogent is advertising 3 different prefixes, right? So it is advertising 10/8, 40/8, 80/8. And level 3 is announcing 10 and 40/8, right? So as you can see, the level 3 and Cogent have 2 prefixes common, and Cogent has 1 prefix that is unique, which is different from level 3, right? Now, if we want to make sure that we're not breaking this global routing while enabling this type of flexibility, then we need to make sure one simple thing here, that if there is a traffic coming in whose destination port is 80, but the destination IP is 50.001, right? Which means that it belongs to 50/8 prefix range, right? Now, as you know, that the Google's program is that if it matches on destination port, it will forward to Cogent, right? But as you can see, Cogent didn't advertise prefix that belongs to 50/8, right? So Cogent actually does not know what is the route to a prefix or an IP address that is in the range of 50/8, right? Or 50.001. Cogent does not know the route to this IP address. So if the Google program is applied as is, then this packet will go to STX. STX will forward it to Cogent, but because Cogent does not know a route to it, this packet will get dropped, right? And this is one simple example of how we can break the global routing if we are not careful about how we apply these policies or programs, right? So to make sure that we are safely interoperating with BGP, what SDX needs to ensure is that this packet is not forwarding to Cogent. So Maggie's question is, can you explain again why Cogent will drop it? So Cogent will drop it because it does not know a route to the destination IP 50.001, right? So Cogent's routing entries will be because it has advertised these three prefixes 10/8, 40/8, and 80/8. When a packet will come in, it will try to match on these prefixes, and based on that, it will figure out what will be a next hop, and it will make the forwarding. But if it does not, if its routing table does not have an entry for 50.001, then it will just drop that packet. Okay. All right. So how can we fix this problem, right? A naive solution here can be that we augment this program, right? So it is saying that Cogent is advertising like this traffic, port 80 traffic has to be forwarded to Cogent, and if Cogent has advertised these three prefixes, then what we can do is that we can augment this program such that it matches on all the prefixes that Cogent has advertised, right? So I will say I will, rather than writing one rule or one program, I will write three programs, which will iteratively match on port 80 and then each of the prefixes that it has advertised, right? So now you might be asking or thinking that, hey, why don't you just write this destination IP in 10/8, 40/8, 80/8 as just one rule, right? But such unions cannot be expressed as an open flow rule, right? Because open flow will be matching on destination IP, and then it can match on, it can do this prefix matching, but it cannot do this random bit matching, right? So it cannot just match on union of 10/8, 40/8, and 80/8. So that will technically have to be translated into three different open flow rules, right? So this will result in an inflation by factor of 3, at the SDX switch. For very simple program, if you have to match on all the prefixes that particular network has advertised, then you're talking about a significant inflation here. Just to give you a sense that I am using this as a very toy examples, like Cogent technically will be announcing hundreds of thousands of prefixes, right? So if there are a lot of policies at the exchange point or at the SDX which are sending or forwarding traffic to Cogent, then we are talking about a huge inflation factor, which will be unsustainable if we go with this approach, right? So clearly, we are looking at a huge scalability challenge here that so far we talked about just 3 networks, bunch of prefixes advertised, but like in reality, we are talking about a setup where we will be handling programs from hundreds of peers or hundreds of networks, 500,000 prefixes, and then rules that will be matching on multiple header fields, right? So we are up for a huge scalability challenge here. And the question is, like, how can we compile these programs for hundreds of peers and 500,000 prefixes, match on multiple header fields? Let's try to revise what type of resources we have here, right? So at the exchange point, we have replaced the conventional switching fabric with a programmable switch. It provides, or it matches, or it can technically match on all headers, but it has limited state, right? And this is something you can intuit from the fact that because you're being flexible in terms of how many fields you can match on, that has a direct impact with the same cost that limits the amount of entries that you can have, right? So because you are using TCAM memory for enabling these type of match action rules, and TCAM is expensive, so if you are, in some sense, when you're matching on all headers, you are expanding horizontally, so that will, with the same budget, that will limit the number of vertical entries that you can have, right? So this is order of 100K, and take this number with a grain of salt, because these, I guess technology improves, these numbers keep on changing, but those, they don't change by orders of magnitude or something, right? So there are incremental changes. Maybe 100,000 becomes 200,000, 500,000, maybe 1 million in the best case, but it is still limited. And if you can buy, or you can build a switch which can support a huge state, but that will be very expensive, right? So this is kind of like relative from cost perspective. But At the exchange point, you also have all the other participants that are bringing in their conventional Cisco Juniper routers, and they're using it for peering, right? So these routers are capable of only matching on destination IP addresses, right? So they are not supporting match on other header fields. So you cannot really write a policy, say, match on port 80 or match on port 443 or 53. That type of flexibility does not exist, but it can match on destination IP addresses, and it can support more state, right? Because now, as I was saying, that it is less, like horizontally, it is less, rich. Then it can support more with the same budget. It can support more entries vertically, right? Which means like more number of entries can be supported in the router. So from SDX perspective, the scalability challenge is that how can we leverage or make the best use of these two different type of resources that we have. One is a programmable switch, which is very flexible but has limited state. The other is a router, which is less flexible because it only allows you to match on destination IP addresses, but it has relatively more resources, or it can support more number of entries. Right? So, the key idea that SDX tries to follow is that why don't we offload the complexity to the packet itself, right? So right now, and then like this is a bit of a subtle argument, so bear with me. Right now, when we talk about the program augmentation, then we are pushing all the complexity on the switch, right? Then the switch will match on port 80, and it will match on all the IP prefixes that Cogent has advertised, right? So there is a huge inflation that is happening at the switch. The argument that the SDX is making is that why don't we offload this complexity from the switch to the packet, right? So when the packet is coming in, it is carrying the information that it has some destination IP which belongs to a prefix 10/8. But in addition to this information, which is in the destination IP field, what if a packet also carries some meta information, right? This meta information, if it carries, and this is a hypothetical argument, but like if this meta information carries this information, that this packet is actually reachable via Cogent and level 3, right? Why via Cogent and level 3? Because this packet is belonging, like its IP address is belonging in 10/8. And notice that 10/8 is advertised by level 3 and Cogent both, right? So that is why if somehow this packet is carrying an information which says that, okay, this packet is technically reachable via Cogent and level 3, then the decision at the SDX is very simple. It can match on destination port for port 80, and then match on whatever metadata that represents Cogent here, right? So if the metadata says like it is reachable via Cogent, and then it can match on that specific attribute of the metadata before forwarding this to Cogent, right? So this is the key idea of SDX. And like now we're talking about, like what is the pros and cons of such a design, and like, how can this be enabled? So reachability attributes is the information that we're trying to encode or add to the packet's metadata. Let's talk about what that attribute is all about. In simple terms, it is the set of valid next hops for each prefix, right? So if every prefix or every packet, it carries information that, okay, what are the valid next hops or routers to which it can be forwarded, right? Again, recall that the announcement, the BGP announcement made by the level 3 and Cogent are here, such that 10/8, 40/8 are advertised by level 3, and 80/8 in addition to the other two prefixes are advertised by Cogent, right? So the reachability attribute is if the packet is belonging to 10/8, then the attribute is level 3 and Cogent. 40/8 level 3 and Cogent, 80/8 only Cogent, right? So these are the reachability attributes that are of interest for us. And then if we can find a way in which we can encode these reachability attributes into the packet itself, then the like a very strawman approach can be that we can assign 1 bit for each of those participants, right? So if there are 100 participants, then we will require a metadata of 100 bits. And then, or in this case, because there are just 2 participants, then 2 bits should be fine. And then the attribute for the prefix 10/8, because it can be forwarded to both level 3 and Cogent, then it will be 1 1, 40/8 will be 1 1, and 80/ will be 0 1, because it cannot be forwarded to level 3, right? So this is the reachability bit mask that can actually be added to the packet, as we were talking about the metadata which the packet should carry, right? If the packet is carrying this metadata, then it becomes very simple how we can enable this policy, how we can enable safe interoperation with BGP. That if you have a policy destination port 80 forward to Cogent, and the Cogent is the second bit in this bit mask, then the augmented policy or program should be that, okay, If the metadata, I don't care about the first bit, but if the second bit of the metadata is 1, then I can safely forward this traffic to Cogent. And this type of augmentation is very easy because technically I'm not requiring any additional rule. I'm just augmenting that existing rule. So I don't require any additional entry in the switch, right? And this simplifies the match action rules that we have to implement at the exchange point, right? So now I think you might be wondering, because you have read about the SDX paper, and SDX paper does not have this scheme, right? So it had a different scheme. So now I'll go back, and maybe this is a question for you folks. Tell me how what type of reachability attributes are like discussed in the SDX paper, the paper that you read. How is it different from what we're discussing right now? So you remember the concept of forwarding equivalence class in the SDX paper? Anybody can tell me what that is? Give it a try. Okay, let me help you folks with that, right? So the idea of, maybe we should go here. The idea that was discussed in the SDX paper was this concept about forwarding equivalence, right? And it was from the perspective of prefixes. So if you look at, in this very simple example, if you look at 10/8 and 40/8, right? So they exhibit similar behavior that both of them can be forwarded to level 3 in Cogent. But 80/8 has a different behavior, right? So in this case, when we were doing the augmentation, yes. So in this case, when we are doing the policy augmentation or program augmentation, then rather than writing two different rules for 10/8 and 40/8, we can group them as one, right? Because they have the same exact forwarding behavior. That's why we can group them in as one, right? And rather than matching on the destination IP, we can match on the metadata, which represents this both 10/8 and 40/8, and that will help us reduce the number of entries. Like in this case, inflation factor will be 2 rather than 3, right? And as you can imagine that, given the diversity of prefix advertisements that you have, that approach might not be a very effective approach, right? And that is something which is the difference between the SDX work and the ISDX work, which was how do you encode this metadata information, right? So the SDX idea was that you will, enable this forwarding equivalence and then look at the set of prefixes that exhibit the same forwarding behavior, which is the set of, what are the next hops, or what are the networks that are advertising these same set of prefixes. And it's not a total waste of an idea, because forwarding equivalence is a common practice. But the ISDX paper actually showed that given the richness of the SDX policies or the SDN policies that you want to express at the exchange point, it might not be as effective as thought. And that's why we need to do something different, right? And that's why this idea of reachability attributes was conceived as part of the ISDX project. And then the idea was, okay, if rather than focusing on the prefixes, what if we focus on the next hops itself, right? Where they have to be forwarded. And so, a naive approach is that we assign 1 bit for each of the SDX participant, and then just, create this bit mask and then match on those bit masks, which simplifies the rules at the SDX, right? So this is the key idea. And as you can notice that if I'm capable of assigning 1 bit for every SDX participant, then I don't require any additional entry, right? So however, whatever is the number of entries that are corresponding to the SDN programs that each of those networks have expressed, I will only need those many number of entries, right? There is no augmentation or there's no inflation here, right? But the metadata size can be a problem. That if there are hundreds of participants, then you will require hundreds of bits of metadata to be added to the packet. And if you're adding hundreds of bits to a 1400 bits of packet, then you are adding a significant overhead to enable such an approach, right? So as a result, this type of strawman scales really poorly. if you have hundreds or thousands of IXP participants. To counter this problem, ISTX came up with this idea of hierarchical encoding, where it divides these reachability attributes into clusters. And so first it matches on the cluster, and within that, basically it matches on the specific ISP or a specific network. So like that hierarchical matching is if you do a hierarchical match, then you will require more number of entries because you have to first match on the cluster and then member of the cluster. So that will increase the number of match action rules that you have to write, but that helps you reduce the number of bits that you require for the metadata, right? So this is the core essence of hierarchical encoding. If you're interested in learning more about that, I will highly encourage you to read the ISTX paper. I think it's a very nice intellectual piece out there about the hierarchical encoding algorithm. But that was the key idea behind the ISTX, where this encoding scheme enabled us to reduce the number of bits that are required for the metadata field. And as a result, we were able to reuse an existing bit or existing field in the packet. So technically, STX does not include or does not add any additional overhead in terms of number of bits that a packet has to carry, right? It basically reuses the source MAC field of the packet, because source MAC is not as important field when you're looking at the STX, or at the exchange point. So that's the field that the STX is reusing, or ISTX is reusing. So this encoding scheme is very effective because it only requires 33 bits if you have around 500 to 600 participants, which is something which can easily fit into the 64 bits that are available for a MAC address, right? So that was a huge win from practicality perspective, and putting into perspective, this was first of its kind system. So I won't say that it has been a huge practical success that all the exchange points have adopted STX, but it had a huge impact, and we'll talk about that later. But this was one of the fundamental reasons why it was impactful, that it didn't require any additional bits to be added to the packet while it was enabling this metadata to reduce the complexity at the switch, right? So talking about the performance, the numbers, the result that you see here is coming from an experiment where there were more than 500 participants, 96 million routes that were advertised for 300,000 IP prefixes at world's one of the biggest exchange point in the world, right? So the baseline result is the one which shows you how many entries you need. If you basically it's a representation of the STX programs that different networks have written, right? So how many match action table entries you will require if you just execute the STX programs that different networks have expressed, right? And then if you do the naive augmentation, which we discussed about matching on each prefix that each of those networks have advertised, then we're talking about an overhead of 68 million, right? And as you can imagine, 68 million supporting 68 million match action table entries is not feasible. As we saw, 100K is basically the upper bound for most of these switches, at least around the time when STX was conceived. So in comparison to that, STX is actually able to bring this number down to 65,000, right? So there is around 3 orders of magnitude reduction with these encoding schemes that we have. As I mentioned earlier, that this only required 33 bits. So with 33 bits, it was able to make sure that the number of entries is less than 100,000, which was kind of like the upper bound from practical perspective. And compared to the baseline that you had, 62 versus 65, so you only required 3,000 extra TCAM entries or match action table entries in the data plane to enable this, right? So from 500-bit metadata, we are able to reduce it to just 33 bits, and the number of TCAM entries that you additional TCAM entries that you require is just 3,000, right? So this is kind of like an interesting result, and also, as I was saying earlier, that because the switch constraint was around 100,000, so this actually means that it can run on a very cheap commodity hardware switch. You don't really need a sophisticated or expensive switch to make this work. So before I move forward, I think I should give you folks a chance. Any questions? Is the difference between SDX and ISDX clear now? Okay, I think let's move forward. So I think like so far we talked about that, hey, a metadata can be added to the packet and then it will only require 33 bits, but we didn't talk about the mechanism of how that metadata can be added to the packet. And let's try to spend some time and understand how that can work. Recall that at an exchange point we have participant who brings in their BGP router, and those BGP routers are connected via the SDX switch, right? So whenever router will have two types of entries, right? One entry will be matching on IP prefix, and then that entry will tell you that what is the next hop IP address, right? So in this case, suppose if this router, BGP router is Google, and it has to forward traffic to Cogent, then the next hop IP address will belong to IP address of the router of Cogent, right? Is that clear? So there will be a forwarding information base of fib entry in the router, which will match on 10/8, and it will say like, okay, the next hop IP address is something that belongs to Cogent, right? But then because this is a layer 2 switch, then it has to go through the layer 2 part of the network, or the medium access part of the network, where it has to figure out that, okay, for this IP address, what is the MAC address, right? Like, because it can only forward it to a particular MAC address in the network, right? So because it's a layer 2 network, so it will use an ARP protocol, which I believe you have read in 176A as well. So ARP is an address resolution protocol, and it will do a translation between the IP address to a MAC address, right? So these are the two processes, like the protocol that the router is going to use to translate the destination IP address to a next hop IP, that will be using the BGP protocol, right? And then it will use the ARP protocol to translate the next hop IP address into the next hop MAC address, right? And this question can be composed or combined together in a way that every router will be requesting that what is the next hop MAC address for a particular prefix, right? So 20/8, if the packet is belong to 20/8. So this is a question that every router will ask SDX controller, right? Using these ARP protocols and the BGP protocols, right? And then it can have an entry like the now SDX controller, rather than reporting an actual MAC address, it can report the metadata value, right? And I'll correct myself. I said earlier about that we can reuse the source MAC. It is actually the destination MAC. Now I recall that the destination MAC is something that we are leveraging in this framework rather than the source MAC, right? But technically we can reuse the source MAC as well, which means that we technically have 128 bits to play with, but we were able to just make it work with the destination MAC address field, right? So now this metadata, which the STX controller is going to tell this router, will be the one that will be added to the packet. In a sense, like it is intrinsically added, that it is the destination MAC address field in the packet that carries the information about the reachability, right? So the rule that we were looking at earlier, maybe I should go back a bit. Yes. So here, when it says the metadata equal to *1, so technically the rule will be that when the destination MAC is *1, right, which means like if the second bit of the destination MAC address is 1, then this packet can be forwarded to Cogent, right? So that's how this metadata match is going to work in an real SDX implementation. And recall that border routers can match on millions of IP prefixes. That's what their job is. So there is literally no change that is required at the border routers that are placed by different networks, right? So they are operating as usual. They're using the BGP protocol, they're using the ARP protocol that they would have used at any other exchange point as well, right? But the only difference is that rather than reporting a physical MAC address, the STX controller is actually reporting a metadata, like a virtual MAC address, which carries the meta information, right? And this metadata information is then used by the IXP to enable this type of flexibility. Okay, so we can summarize the SDX work right now, but I think like before I do that, again, I'll give you an opportunity to ask any question. Is there any confusion about the mechanism here? What is our protocol? What is BGP protocol? Any questions here? Is this too overwhelming? Is this a lot of information for you to process? Okay. So Maggie's question is the strawman attaching the bits for metadata, or is that different? So strawman is basically a conceptual idea. It cannot be realized because you are requiring a lot of like a lot of bits to be added to a packet, right? So think about it from this perspective that 1.4 KB is the typical size of a packet, and if you have say 1000 participants at the exchange point, right, then for every packet you're using or you are adding 1000 bits over around the 1400 bits of the original packet size, right? So that's a huge overhead. So but if like if there was a metadata approach that was possible, then there are two questions, right? How will you enable this metadata approach, right? So can you like will that require you to do some type of encapsulation, right? So you might have to use a different type of protocol so that you can make this work, or add this metadata, but that will require making some changes to the routers that the participants are bringing in, right? So the intelligence of STX here is that it is, because it is reusing a destination MAC address field, it is using or basically leveraging the ARC protocol and BGP protocol to pass this metadata information, which is then encoded into the destination MAC address field itself, right? So it is not requiring any changes because it is reusing the existing set of protocols, right? But that said, the metadata, the naive, the strawman approach, metadata approach can technically be enabled, but that will require some changes to the participants router as well, right? And also, like, even if that is the case, then the overhead is still going to be huge. That like if you are say if you have a packet of size 1500 bits and you require 1000 bits of metadata to be added to it, that's a huge overhead that we're talking about. So it was not a sustainable idea, but yes, like in practice or technically it can be done, but it's not sustainable. All right, thank you for that question. Any other questions? So I think something that I want to bring up, that I saw that some of you were very disappointed reading the STX paper, saying that, hey, this is not real, or it has not really transitioned into any practice. So I might want to give you a brief history of how the STX project was kind of like conceived, and like what was its journey. And I can say that because I was part of that journey as well. So STX was something which was like came out from the exercise that when people looked at the software defined networking, uh, people like me and my advisors and like other researchers were frustrated with the fact that software defined networking just focuses on data center networks, right? And it is by design it's suitable for data center networks because you own the full network and you can do whatever you want, right? So you can change the switches, you can buy those devices and make those changes, right? But the question or the thought process was like, is it possible to take the advantages of software defined networking and change the interdomain networking, right? So interdomain networking or internet, I guess like it's a very challenging part. And as I was saying at the early stages of this class, that the border gateway protocol was conceived in 92 93, and it didn't really change at all until 2013 2014 when like STX was conceived, right? So there were incremental ideas that came in. People were just forcing traffic engineering policies by changing some attribute fields of the BGP, and that was all leading to chaos in practice. There were so many route leaks happening, so many hijacks that were happening in the BGP. The internet was very unstable, right? Forcing these traffic engineering policies on top of BGP, and those policies were also very unpredictable. So there was a clear need, but there was not a clear solution, right? And I won't say that SDX kind of like changed the world. It didn't, but it was a stepping stone in the right direction, right? So a lot of ideas that SDX generated were then adapted by different other systems. So there were a couple of startups that were built around the SDX idea that were trying to sell software switches. Rather than these hardware switches, they were trying to sell the software switches. They were trying to provide these programmable transit services and all those things. So there was a lot of ecosystem that was derived around the SDX ideas. And then, as I mentioned, that Google and Facebook, when they built Espresso and Edge Fabric, then they adapted the ideas that were developed in SDX as well. Right? Another use case that was kind of like instrumental in making SDX a bit more real and practical than it was, because SDX came out in say 2014, and then ISDX came out in like 2016. So between this time period, what happened was that the government was very interested in this research direction in general, and they basically created $25 million funding to support research on this topic. And out of that, I think not just NSF or one government agency, there was NSA, National Security Agency, that was also interested in it, because they wanted to build an exchange among all the other government agencies, right? So when FBI is talking to NSA or some other organizations, they wanted a lot of flexible policies that need to be applied at the exchange. Like, not, this is not public internet, right? So this is internal to the government agencies itself, but they wanted to apply a different set of flexible policies on the traffic that is exchanged between the different government agencies. So for them, SDX was a very attractive tool because they can enable it by just making changes to one couple of switches or switching fabrics that they had in the network, right? So that that supported our program. And typically when you do research, then you're focused on developing research prototypes, writing papers. But then after 2014, when SDX got published and we got the attention from a lot of agencies, then they supported us with a lot of engineering firepower, right? So I basically developed these prototypes, wrote papers, but then I also provide these design guidelines for the engineers, who were then responsible for transforming, open sourcing all this. So this is all open source, even though it was used by government agencies. But then they were also responsible for knowledge transfer of taking all these software prototypes that were out there and productionizing it so that it can be deployed in different agencies, right? So that was very helpful. And there are a lot of exchange points that use SDX right now, but its real impact was when different content providers like Google and Facebook started adapting the ideas and building a version of SDX of their own, right? So this has kind of been a trend in general, that big changes happen when big players kind of adapt these ideas. So but SDX was not designed to just help Google or Facebook, right? It was designed so that anybody who's a participant at these exchange points can benefit from programmability offered by software-defined networking. And wherever, but at all the exchange points where this is actually deployed, so the network operators do have that type of flexibility. And this might also be an interesting thing for some of you who are still looking for a project, that there is not a version of STX or ISTX that is there for P4, right? So this is something which was developed in 2016, 2017. P4 was not mainstream back then. So there is only implementation of STX or ISTX with OpenFlow targets, right? But now things have changed. PISA-based targets, so the RMT targets are more popular. So if somebody is looking for a project, making ISTX work for P4 switches might be a very low-hanging fruit that somebody might be interested in, right? And I'll be more than happy to fill you up on what needs to be done. But that is one potential research project or one potential project that you can take for this course. All right. Oops. Yeah. So before we leave, I just want to conclude that software-defined exchange point was a very promising software prototype that was developed, which identified this internet routing problem, which I would say was multi-decade problem, and it provided a more legitimate solution to that. It solved a lot of challenges in building a deployable SDX, and this is very important because when we just advertised or talked about the idea at a high level, when we just proposed the idea that, hey, this is what we want to do, everybody was said hey, this is a very simple idea, right? So your goal is to just replace a switch and then replace a route server with an SDX controller. How difficult that can be. So one of our contribution in this space was also to highlight the real challenges in building such a deployable SDX, right? So things that we learned about interoperability with BGP and different scalability solutions that we were exploring, it required 2 research papers to solve that problem, right? So that basically opened up the research space a lot, and there were a lot of follow-up papers. If you look at SDX, it has been cited more than 400 times, right? So there was a lot of follow-up that happened on such a work, and that laid the foundation of many research prototypes and many research artifacts that were actually productionized as well. So yeah, I think if any of this is interesting, feel free to reach out to me if you're interested in pursuing this for the term project as well, or in general, if you're interested in learning more about SDX or ISDX, feel free to reach out to me over Slack, and I'll be more than happy to answer your questions. All right. So with that, I think we can end the lecture. Any other questions before we leave? stop the share. I think this was recorded, so we're fine. All right. All right, no questions then. See you on Wednesday.
Thank you.
Thank you.